we lift our heads to the sky at night, we simultaneously see the brightness of all the stars that our eyes can reach. It follows that, if its light were not already with us, a star could not be seen directly. The problem seems to be in the observer, as he is dependent on a messenger whose speed is fixed and limited. In any case, the time taken by this light to travel through the space that separates us from the stars would not matter, because, if it existed, this time could not be measured directly. Thus, as the beginning of the counting of time is fixed in the position of the observer and not in the position of the stars, the future cannot be remembered. It is as if the light was simultaneously in two places in space at the same time, without the need for departures or arrivals. In order to see a star, it would also be necessary for its light to be previously packed or quintized. Whether it would have quintized on the way to Earth cannot be known, but it is more likely that quintization is, basically, an intrinsic motion. That is, the quantization would be contained in the observer himself, by a principle of excluding access to what happened in his future. Although quantization is a process that would occur at the subatomic level of particles, there would be no irradiation until this phase is complete. You couldn't see a particle until the moment it took its quantum leap and the light scattered. It is at this moment that the electron recoils and the quantum spreads out in the form of a photon of light. As our dependence on the local scattering of light is the same in the case of distant stars as well, it can be said that when it comes to observation, infinitudes become equal at all levels of matter. Another notable aspect of quantization concerns time. It was imagined that an electron would be sucking energy from a metal plate until it took its quantum leap. For that, the electron should use some time interval, no matter how small. However, at the beginning of the 20th century, it was demonstrated that the quantization of all forms of energy does not take time. As we usually evaluate space through electromagnetic radiation, as is the case with its use to measure time and distances that separate us from galaxies, the absence of time, in the stationary phase of light quantization, grows in importance. As has already been said, to see a distant star it is enough to lift our head to the sky on a dark and cloudless night. In this case, the time that the light emitted by this star would have traveled through space in a previous moment is not being taken into account. This suggests that the quantization of light energy would be able to reverse the direction of the arrow of time, especially when it comes to our point of view. The inversion will happen when the light spreads out and allows the illuminated particles to be seen in relative and continuous motion. It would be as if during its packaging, the light remained connected with the source, a process that would not involve any measurable time interval. Modern theories maintain that the universe would have started to expand in the moment after the Big Bang. The main subsidy for the elaboration of these theses is the cosmic background radiation. There is no other source of information available about a singularity that would lie 13.7 billion years in our past. As the cosmic background radiation initially needed to be quantized to become subsequently traceable, and the process would not have consumed any measurable time interval, this had two immediate consequences. The first is that the behavior of space merged with the behavior of light, no longer allowing direct and exclusive access to space. This includes the description of its geometry, which started to be made through light. The second is that, at least when it comes to the observer's point of view, there would have been an apparent reversal in the direction of the arrow of time. From its local scattering, the light would have started to point, continuously, in the direction of the past. As the observer is dependent on the scattering of light after the quantization phase, to be aware of what happens around him, it is said that he has become dependent on his memory. That is, for him, there is only what can be remembered. This is a good reason to justify the finding that, in post-Big Bang spacetime, electromagnetic waves would be continuous and seem to disrespect the photoelectric effect. Thus, we could have been led to the natural interpreted error that the light in the cosmic microwave background could be followed both in the direction of the past and in the direction of the future. Since the future has yet to happen, light seems to directly connect us only to past events. Intuitive thinking, which would have given rise to inflationary theories, could have resulted from the necessary energy quantization phase, to which cosmic radiation would have previously been submitted. It is a unanimous conclusion of astronomers that the universe would have gone into continuous expansion after the Big Bang in the presence of accelerating the motion of galaxies. If the expansion had been confused with the retention of time in the energy quantization phase, this would place the Big Bang in the universe's present, relating it to the scattering of light. That would be an informational Big Bang, not a cataclysmic explosion. At the moment of light scattering, the arrow of time would have been inverted in our position, as if during the entire phase of its packaging, the light had remained connected with its source, in an unrecordable way. Inflationary theories would be supported by the fusion between the behavior of space and light. If the light shifted towards the red, space would follow this movement, stretching. However, when you stretched space, you would expect an increase in potential energy. Translating, light could not accelerate at this stage. This would compromise the claim that acceleration would follow redshift. When the behavior of space is confused with that of light itself, its expansion would be equivalent to negative work, resulting in deceleration. If light movement existed in this phase, it would have to be retrograde. Galaxies should slow down. The retention of time in the quantization phase suggests that all cosmic events would be placed virtually in our future, regardless of the considered level of matter. It's just that we are dependent on the local scattering of light. As you could not interact with matter in real time, the concepts of future and present become equivalent. The past, in turn, would be an illusion resulting from the same trilogy, because, if we could only look at the present with a delay, that means that we would have been thrown back in time. The absence of measurable time in our future would have stripped space of its ability to directly communicate changes in its geometry. In that case, the space would have turned into a phantom entity, or one that couldn't be touched. The moment when the electron recoils and the light photon scatters during the quantum leap would be equivalent to the second phase of the harmonic movement of light, when it would tell us that the elastic band of space was being left free to contract. It is here that the presence of acceleration of movement would be noticed. Acceleration should accompany the contraction of the length of the rubber band of space, but what you see in the practice of Doppler is the presence of acceleration in its expansionary phase. Remember that we are assuming that, when it comes to observation, there would be no difference between infinitudes, as both atoms and stars would depend in the same way on remote tracking of light. Without the existence of measurable time, in the first phase of the radiation's harmonic motion, light scattering would have overtaken the contraction of space and revealed the expansion, as if it were happening in real time. With that, the two phases of the harmonic movement would have become virtually continuous, due to the exclusion process between them, generated by the timelessness of the energy quantization phase. If you see the rubber band of space stretching, you cannot see it contracting simultaneously. The attitude of considering that space would behave similarly to a spring or a rubber band has already been raised by a good part of the scientific community. The model suggests that, during the universe's expansion, galaxies would not abandon their positions in space. They would move away from each other faster and faster due to the stretching of the space that welcomes them. There is a possibility that there's an interpretation error in this model because it disregards the radiation packing phase, the same radiation that we use to measure the elasticity of space. When evaluated by the cosmic background radiation, the expansionary phase of the universe would correspond to the first phase of its harmonic motion. Thus, we would have to take into account that the work done in this phase would be negative, with an increase in elastic potential energy to the detriment of kinetic energy. That is, the movement would tend to collapse, as would happen in an implosion. If the universe were in continuous expansion at that moment, the description of the event through light should suggest that the galaxies would be entering retrograde motion, which does not happen in Doppler practice. If we take into account that during the stretching of space there would be a complementary contraction of time, we would be, unintentionally, falling into the concept of timelessness of the quantization phase of light energy, which would not be a mere coincidence. Thus, we could assume that the expansionary phase of the universe would be acting, in its own time, as a huge eraser of information. That doesn't mean the information wasn't there, though. This problem, as noted, is related to the existence of an isolated observer who uses cosmic radiation as a source of information. As he is dependent on its memory, and, consequently, dependent on the direct measurability of time, the expansion could only be evaluated outside its own time. We could ask if this is not exactly what happens in practice.